Yes, the recording has started. Okay, and so I would like to announce the next speaker. It's Ben Blum-Smith, and the title of his talk is Degree Bounds for Rational Invariants. He is from Johns Hopkins University. So, please, Ben.
Thank you so much for having me. I'm very excited to be here. I'm honored for the invitation, and I'm excited to share this work with this community in particular because the bibliographies of especially one of the two papers that I'm going to be presenting on are like full of your names. So this is work very much inspired by a line of work that you all have been part of. So I'm really excited and happy to be here. Let me just go into full screen, which is going to prevent me from seeing you or how I look, but I'm just going to hope for the best. Can you guys see that?
Yes, now it's full screen.
Awesome. Okay. So this is based on two papers. The first is joint with Afonso Bandera, Joe Khalil, Jonathan Nowsweed, Amelia Perry, and Alex Wine. That paper provides the motivation for the main inquiry and is also the source of the first result I'm going to share with you. But the main line of inquiry and all the rest of the results are from the second paper, which is joint with Thais Garcia, Rawan Hidalgo, and Consuelo Rodriguez. We got the usual characters. We're going to be dealing with a finite group. K is an arbitrary field. Usually or often G will be abelian and K will have characteristic not dividing the order of G, but I'll say that explicitly when it happens because some of the results are more general. The rest of this has already been in like most of the talks so far. So the next few slides are going to be things that you pretty much already know, but they're part of the story, so I'm going to include them. The Noether bound, we know a priori from Noether that the algebra of invariance is generated by its elements of degree at most the order of G, and because of this, we have a name, beta, for the degree you have to go up to before you've collected enough invariants to generate the ring. We know a lot about this number. Many of you have participated in the program to study this number. This is just a smattering of results from the last 25 years about it, but actually several of the talks that have already happened in this conference include results about beta. So we love this thing. For some applications, beta is asking for more than we need, though. We have the notion of separating invariants, which again, I think has been mentioned in like, I don't know how many talks so far in the conference. So I'm not going to define it, but if returning idea introduced by Dirksen and Kemper, but sort of returning to the roots of invariant theory, suppose you just need enough orbits. Sorry, if you needed enough invariants to separate orbits. So in the last sort of 20 years, there's been a research program to study what that does to the question of degree bounds. So how high degree do you need to go, not to actually generate the ring, but just to separate orbits? Maybe it's lower. And here is a smattering of results that we know from the last 20 or so years on that. Again, all the names on this slide are basically people at this conference. So, this is the context of degree bounds. So the thesis of this talk is that these two numbers that I'm about to define are also very interesting, also potentially useful, and much less studied. So I'm hoping to convince you to study them with me. And I'm going to share with you what we've found so far. So here are the numbers. Beta field. So this is the minimum degree such that you've connected enough polynomial invariants to generate the field of rational invariants as a field. And rational beta field, or beta field R, which is the minimum D you need such that if we define the degree of a rational function to be the sum of the degrees of its numerator and denominator, Now we let ourselves use rational functions to generate the field too. So what degree do you have to go through before the rational functions of less than or equal to that degree generate the field of invariant rational, the invariant rational functions of less than or equal to that degree generate the field of invariant rational functions. So the difference is that beta field requires the generators to be polynomials of small degree, and rational beta field allows the generators to be rational functions of low degree, but in both cases, we're trying to generate the field of rational functions. So, right, I'm also just going to quickly define two other numbers, gamma field and gamma rational field. They're the same definition, except instead of actually needing to generate the field of rational functions, you're just asking for a transcendence basis. So gamma field is the degree such that the polynomials of or less than or equal to that degree contain a transcendence basis. And rational gamma field is the same thing, only rational functions of less than or equal to that degree, where, again, I'm defining the degree of a rational function as the sum of the degrees of the numerator denominator. You might wonder why I chose that definition. I'll say something about it later. At any rate, the notation is inspired by notation that Dirksen and Kemper use to talk about the degree you need to go to before you can get yourself a system of primary invariants. But I just have to make a notational note, especially after Elmer's talk yesterday, that this is not the same, not related to Elmer's use of gamma, which means something different. So in this talk, gamma means degree bound for the degree you need to go to before you have a transcendence basis. Okay, so I said I was going to tell you this is interesting, useful, and not much studied. I'm going to take that in reverse order. So I'm going to tell you what I'm aware of that we already know about these numbers. So beta field was defined with slightly different notation in a paper by Fleischmann, Kemper, and Woodcock in 2007. And in the context of that paper, their purpose was to show that the Noether bound holds for beta field, and that's true regardless of characteristics. So even for modular representations where where there's no a priori bound on the generation degree. And actually, the construction they use to prove it is very similar to the construction that's used to prove that the separating Noether number meets this same bound independent of characteristic. And these are related. That's one precedent. The other one that I found is a paper of Hubert and Laban from 2016, specifically focusing on abelian G's acting diagonally. And they give an algorithm to compute monomial generators for the field of rational invariants. And sort of as an aside, they note that they get a bound order of G divided by a determinant of some matrix that depends on the specific way that the action of G on V is presented. And in practice, that determinant is often 1. They weren't really, their purpose in that paper was to give an explicit algorithm to compute generators that have some good properties, and in particular that you can explicitly, they have a rewrite rule to take an arbitrary invariant and write it in terms of those generators. So they weren't really interested in, they weren't really studying the degree bound per se, but they just tossed this off as an aside of the machinery they developed. So as far as I can tell, this is it. There's a few explicit constructions of polynomial generators out there that sometimes note, for a field of rational invariants, which sometimes note what the degrees are. But as far as like general studying of these concepts, this is all I found. Please let me know if you're aware of something I missed. Anyway, I hope to have convinced you that these things are not much studied, but a little studied. So I'm hoping that means that there's appetite for more. Now I'm going to tell you why they are well motivated. So the motivation comes from signal processing. there's a circle of problems in signal processing called orbit recovery or generalized multi-reference alignment, in which we observe a signal that's been corrupted not only by noise, but also by a random group element. So here are two examples. Multi-reference alignment, the namesake. The signal is a vector in a real vector space. It's transmitted through a noisy channel that is not only noisy, but also fails to keep track of which coordinate came first. It only tracks the cyclic order. So you're only seeing the signal up to cyclic shifts. So there's implicitly an action of Z mod dz, where d is the dimension. The other motivating example, very important motivating example, is a biological imaging technique called cryo-electron microscopy, in which you freeze a thin layer of a substance that you want to image the molecules of, and then you zap it with an electron beam, and you look at the images you get. So because the molecules that you want to image are in unknown orientations, in addition to the images are incredibly noisy. Like if you look at them with the naked eye, it looks just like static. But in addition to that very high noise level, there's also, you don't know the orientation. So there's implicitly an action by SO3. In that case, I'm going to sweep this under the rug for the sake of this talk, but there's also the fact that you're projecting to 2D, but I'm not going to include that in the formal setup of the orbit recovery that I'm going to discuss with you. Here's the formal setup. You've got a vector space of a real vector space of signals. You've got a signal. You've got a compact Lie group acting on the vector space, and you've got a fixed noise level, which we're going to think of as high based on the motivation. What we observe is the signal transformed by that randomly selected group element that is randomly chosen according to Haar measure, and then added to that noise vector drawn from a Gaussian, which is scaled by the noise level. And the goal is to recover the original signal. We can't do better than up to orbit because of the group action. The question is, how many samples in that setup do we need to see before we have hope of accurately measuring the orbit, accurately recovering the orbit of the signal? Because if the noise level is high, one sample obviously tells you nothing. So how many samples do we need to see? And in particular, how does the number of samples we need to see to do that job scale with the noise level? So here is the answer. And this is an informal statement because it's a statistical signal processing theorem. And so the technical details are off topic for this conference. But this is the main story. The answer is the number of samples you need to see is on the order of the noise level to 2D, where D is the minimum degree of the G invariant polynomials that are able to distinguish that orbit from other orbits. So this is where the motivation is coming from. That tells us right away that in the worst case, the number of samples we need to see, the sample complexity of the problem, is order of noise level to the 2 times beta sep. And this is useful, but it's horrible if beta sep is large because it's exponential in beta sep. So we might be able to get away with something better if we're willing to work with a generic signal rather than a worst case signal. And this is where you can start to see the connection to the topic that I've posed for us, because there's a classical theorem called Rosenlicht's theorem that says that a generating set for the field of rational invariance automatically separates generic orbits. So that tells us that the number of beta field, which we defined above, is the thing in the exponent for generic signals in an orbit recovery problem. So this motivates an understanding of that thing, because if it's much lower than beta sep, then we're getting tremendous computational savings from working with generic signals instead of worst case signals. And there's very similar reasoning that shows that sometimes you can get away with an even weaker setup where you recover a finite list of possible signals that your signal might be on. And that is exactly the degree of that. In that case, the degree needed to separate a signal from a finite list, a signal and a finite list of other signals from the rest of the signals generically is exactly the degree of a transcendence basis. So this motivates an understanding of gamma field. So for the rational versions of these two things, I don't have a quite similarly concrete motivation for them, but they do provide lower bounds on the ones that I have motivated. And, you know, there's somebody who's going to feel like the rational ones are more natural anyway, because we're trying to generate a field. So why are we restricting ourselves to polynomial generators? To me, it's not a clear-cut case because, on the other hand, degree is a more natural concept for polynomials. So I just think they're both interesting and both worth studying, and we made some effort to study both. So now I've told you that why it's not much studied and why it's motivated, and the rest of this talk is going to be about why it's interesting. So hopefully you will find the following as intriguing as I did when we found it. So consider a cyclic group, order n. Let's work over a field that contains distinct nth roots of unity, and consider the regular representation. For the classical Noether number and the separating Noether number, I'm just going to, for your enjoyment, give you a second to think about what they are in this case. So it's n. It's always
n minus
right?
1.
And for the separating Noether number, this follows from work of Domakush from 7 years ago or so. The classical Noether number, you know, you could convince yourselves of it. I'm not going to try to convince you of this. I think you believe me. I'm happy to, if you want to talk about why, we could talk about why. But anyway, how about beta field? So I invite you to take a second to think about it, what you expect it to be. I'll tell you in a sec. Is it also n? Is it n over 2? Is it square root of n? You ready for the answer? It's 3, regardless of n. So I'm hoping that you think this is as awesome as I thought it was when we figured it out, because I was just like, what? You mean it doesn't even depend on n? And this is actually a special case of a more general result, which I wrote down the proof of. I think I probably won't get time to give you the proof in a leisurely way based on what else I stuffed into this presentation, but hopefully there'll be time for me to at least rush through the proof at the end in like a minute and a half. Maybe I'll have 5 minutes. That would be great. We'll see. Anyway, the claim is for the regular representation of any finite abelian group, the field of rational invariants is generated by the invariance of degrees less than or equal to 3. And actually, we just need the non-modular case. We don't actually need to. The assumption of, in the paper, we stated this under the assumption that I wrote here, but it turns out that only non-modular is needed. I was particularly struck by this because, in general, at least when K has characteristics 0 or bigger than the group order and is infinite, the regular representation always maximizes both beta and beta set, the classical Noether number and the separating Noether number. So clearly something very different is going on in the beta field situation. Also, I will just state a conjecture, which is that the same statement holds without requiring G to be abelian. I have a student working on this, but I'm putting this out into the world. Like if you know, there's reason to think this, feel free to ask me about it. But I don't have a proof yet. So yeah, so that's an exciting unsolved problem. Now I'm going to tell you a bunch of results. So the paper that I mentioned with Garcia, Hidalgo, and Rodriguez is really a first pass at like, okay, this is new territory. Let's try to figure out the basics. So there's a ton. I just mentioned one open problem, but there's like a ton of open problems. So I'm hoping that that you all think this is interesting enough to get involved, because that paper is really like a first pass collecting the, there's more to do. That's what I'm trying to say. So here's some basic stuff. The 4 quantities I defined are related by these inequalities. The first 3 are totally trivial. They're just like, well, if you allow yourself rational generators, well, the rational potential generators contain the polynomial potential generators properly. So you might make it easier to get a transcendence basis, and you might make it easier to generate the field. The second one is because we know in the finite group case that the invariant field is generated as a field by the invariant ring. So certainly if you have enough degree to collect enough generators to generate the invariant ring, you have already generated the field. And the last one is a little bit less trivial because it depends on the converse of Rosenlicht's theorem, which only holds when K is algebraically closed, which says that if a set of rational invariants generically separates orbits over an algebraically closed field, then it generates the field of rational invariants. So that's where that last one comes from. The rest of the stuff on this slide is results that were not very hard, but we didn't find them written down anywhere, so we wrote them down. The first is that base change, even for these things involving field, rather than just rings, like the things here, if we were working with rings instead of fields, these would all be equalities and they would all be trivial. It's a little bit less trivial, but it's basically routine algebraic bookkeeping to show that for the polynomial generators and the polynomial transcendence basis, base change doesn't change anything. And when we allow ourselves rational generators, base change actually does create the possibility of lowering the generation degree, essentially because there exist invariants in low degree over a bigger field that don't exist over a smaller field, because they consist of ratios of semi-invariants that are only defined over that bigger field that has some roots of unity in it that the little field doesn't have. But in the case where there's no non-trivial roots of unity, we can show that actually everything, adding rational generators, allowing yourself rational in addition to polynomial generators doesn't affect anything. So those are like the very first things. And now let's talk method. So in the case that G is an abelian group and K contains distinct order of G roots of unity, then we can use a very common strategy in the study of invariant theory of abelian groups, which is to diagonalize the action so that we can see the action as monomial, acting, all the monomials are eigenvectors for the action. And then we can see the invariant ring and the invariant field, but only in terms of the monomials. So if we take the invariant monomial, proper monomials, we get essentially a combinatorial datum that captures the whole invariant ring. and if we take the whole lattice of invariant Laurent monomials, meaning possibly negative exponents, then we get a combinatorial datum that captures the whole story of the field. And so actually, as an aside, all we need here is the non-modular assumption because we can base change. But we have to keep in mind this might lower the rational versions of the numbers. Anyway, again, this is sort of routine algebraic bookkeeping, but it wasn't written down, so we wrote it down. That the lattice of invariant Laurent monomials captures the whole story. And this, by the way, is why we went with the definition for degree of rational functions that we did. Because if you take a monomial and you take its degree, if you see it as a lattice point, that's just the L1 norm of the point. So we defined degree for rational functions in such a way that the L1 norm of the point corresponding to a Laurent monomial would be the same as the degree. So given that definition, here's what this adds up to. If you take all the points in the L1 ball of radius d, that corresponds to all the rational functions of degree less than or equal to d. And if you take the L1, the intersection of the L1 ball of radius d with the non-negative orthant, then you get the polynomials of degree less than or equal to d. So it turns out that the field is generated by the polynomials of degree less than or equal to d if and only if the lattice of invariant Laurent monomials is generated by the points of L1 norm less than or equal to d lying in the non-negative orthant. That's this one. And similarly, if we allow ourselves rational generators, then we just have to look at the whole L1 ball of radius d. Let d be big enough so that that ball contains a set of lattice generators. And then for transcendence bases, we just need a full set of generators for a full rank sublattice. So we just need dimension many linearly independent generators in the L1 ball of radius d, or dimension many linearly independent lattice points in the non-negative orthant and in the L1 ball of radius d. So this lets us study the question completely in terms of Euclidean geometry of lattices. Oh, wow. I was miscalculating the time there. I have 3 minutes left. Okay, I'm going to go very fast. If in the non-modular case, in the G is abelian and non-modular case, after base changing to where we split the representation, then the representation is split, and it turns out that only the set of non-trivial characters matters, not their multiplicities, and trivial characters don't matter at all. So you can imagine a representation where you've deleted all the trivial characters and deleted every duplicate copy of any other character, and none of these numbers change. So just introducing notation, let M be the number of distinct non-trivial characters. Okay, I have time to give you the main results. That's great. So here's the lower bound. We have a general lower bound. So rational gamma field is a lower bound on all 4 of those numbers. So this lower bound applies to all 4 of the numbers. And the answer is that it's at least the mth root of the order of G. If we relax the assumptions about G, making it possibly non-abelian, and V making it possibly modular, we still have this about gamma field. The proof technique is completely different. Not rational gamma field, but gamma field. So this is a slightly weaker result, and it's also weaker because the root is the whole dimension of V and not just the number of distinct non-trivial representations. We also have an upper bound in the special case of Z mod PZ. So that upper bound is if V has at least 3 distinct non-trivial characters and we're in the non-modular case, then beta field, which is the biggest of those four numbers, is not much bigger than p over 2. So this is interesting because I'm going to skip this comment about the lower bound. The upper bound is interesting because the classical know their number and the separating know their number never go in the non-modular case for Z mod PZ, at least for a field containing the pth roots of unity, these things never go below p for any non-trivial rep. So already the story for beta field is much richer for Z mod PZ, even in the non-modular, let's say algebraically closed case. And it's usually much lower than p. Why is it not? Okay. But that theorem that I gave you is not sharp. Even in the m equals 3 case. So it's an upper bound. To me, I'm making the case that it's theoretically interesting because it shows that the beta field is a completely different story from beta and beta sep, but it's not sharp even for m equals 3. The real bound appears based on computational data to be p plus 1 over 2, one lower. And, oops, why does it, hold on a second. Sorry about that. Full screen. Yeah, here. This looks like it seems to be that this is the real answer. So ceiling of p over ceiling of m over 2. So it decreases as the representation grows. And if this conjectural upper bound is true, it's sharp, and here's the representation that realizes it. But we cannot prove the conjectural upper bound yet, so that's another totally exciting open problem in case you're interested. That I'm out of time, so I am gonna skip the proof of the regular rep thing, unless one of you asks a question about it. I practiced and I think I can go through the proof in about a minute, but it is, I don't know if it's understandable, you know. Anyway, there you go. Thank you very much.
Okay, let's thank the speaker. And are any questions or comments?
Can you say something about this proof?
Oh, I would love to. Okay, I would love to. Let me try to whiz through it. Okay, so the idea is, as usual, you go to the diagonal basis. The diagonal basis has a basis element for every character. You explicitly write down what the degree 2 and 3 invariants are. You name the field they generate. It's evidently inside the invariant field, and you want to prove it's the whole thing. Now you do some cute algebra to show that the nth power, where n is the degree of the group, the order of the group rather, you show that the nth power is in this field for each of those, for each of the bases. That tells you that you're inside a Galois extension that you explicitly know the Galois group of. So you write down what that Galois group is. You identify it with maps from G's character group to roots of unity. And then you ask the fact that it fixes the degree 2 and 3 invariants, what does it tell you about that map? So you explicitly write down the invariants that you explicitly wrote down. You get conditions on the map from them. And you find out that the map preserves inverses, and then that it even preserves the group operation in the character group. So at this point, you've identified an automorphism that fixes K with a character of the character group of G. So by Pontryagin duality, you've identified the automorphisms that fix K precisely with G. So that tells you by the fundamental theorem of Galois theory that your K, which is the subfield generated by the degree 2 and 3 invariants, is in fact the fixed field of G. So that's it. Did I do it in like a minute?
I guess so. Okay,
Thank you.
Matthias, do you have more questions?
No, thanks. Thanks for the proof.
Okay, and Colin?
Yeah, so my first question was identical to Macia's question, so that's beautiful. The second question, at some point you mentioned these applications to orbit recovery and cryo EM, is that right?
Mhm.
Cryo. And but then you talked about doing things for generic objects.
Mhm.
And I have a hard time like fitting generic things in applications. And so how, I was wondering if you could say a few words about how, solving all kinds of questions for generic objects, whatever that means, is still relevant for applications.
So in the signal processing context, it's actually quite relevant because most signals are generic. Like unless that for some reason the signal is coming from a sort of highly structured. The question is, how much structure do you know about the signal? If the signal is really any vector, so for example, for the MRA
Right.
problem,
Okay.
the signal is just a vector, and it's really any vector. So the fact that we know that there's only a Zariski closed subset of bad signals where the degree 3 invariants don't separate them, tells us that almost any vector, any mildly perturbed vector, even if you have a bad vector, a tiny perturbation of it makes it not bad. So, in practice, that's, I'm sort of trusting I come from invariant theory. My colleagues on that paper come from the statistical signal processing side, so I'm trusting them. But their take was, that's the real problem,
Okay.
and for cryo-EM too, you're just dealing with noisy images of molecules. Maybe the molecule has some structure and you know about it, but basically in practice, it seemed that the degree bounds that come from that were the right ones anyway. So this was an explanation for something observed in practice. So I think, at least for those problems, that genericity, meaning being in the complement of something Zariski
Right.
closed, really is most things that you care about.
Yeah, very good. Thank you.
Okay, thank you, Karen, for your question and Ben for your answer. Are any further questions or comments? Okay, it doesn't seem to be the case, so then let's thank the speaker again. Okay, thank you, Ben.
Thank you so much.
And now